Hello everyone. Today in this session of GOCC, we have Velmurugan from IMSc Chennai. He's going to be talking about the minimal polynomials of elements in symmetric and alternating groups, and I'm quite excited to hear what he has to say. So go ahead, Velmurugan.
Yeah, thanks for the invitation to talk here. And yeah, as you can see, I'm going to talk about minimal polynomials of elements in symmetric and alternating groups. And let's get started. So yeah, let's build some notations. Let G be any finite group, and a representation of G by, I mean, a pair rho comma V such that rho is a group homomorphism from G to GLV and V is any finite dimensional vector space over C. And let G be an element of G with having order K, then of course we all know that G to the power K is going to be identity. And since rho is a group homomorphism, so we can see that rho of G to the power K is rho of G is a matrix and rho of G to the power K is going to be identity. With this, we can see that the minimal polynomial of rho of G divides x to the power K minus 1. This is just because we know that over C, the finite order matrices are all diagonalizable. So, and so that just implies that the minimal polynomial is just going to be x minus product of x minus a, where a varies over the eigenvalues of rho G. Okay, so the question is, when is this minimal polynomial is actually equal to x to the power K minus 1? And is it always going to hold? Of course, no. For example, for any abelian group, we know that the irreducible representations are one-dimensional characters. And for that, for any element, we know that the minimal polynomial is just going to be a linear polynomial. So definitely, this is not going to hold in general. So we can refine the question. That's what Teep and Jeliski did as follows. So again, let G denote a group and theta V be any irreducible representation. Then for an element G, we denote degree of theta of G by the degree of the minimal polynomial of the matrix theta of G, and M of G denote the order of G in Z mod center G. And with this, one can ask the following question, which is in fact asked by Teep and Zeliski, namely, can we determine all possible values of our degree of theta of G, meaning the degree of the minimal polynomial of the matrix theta of G? And if possible, all triples G theta G such that the degree of the minimal polynomial of theta G is strictly less than mg. Now here you can note that the less than or equal inequality will always hold. It's just because when we raise this G to the power mg, we know that that's going to lie in the center of G, because mg mg denotes the order of G in G mod center G. So that implies when we raise to the power mg, that will lie in the center. And by Schur's lemma, we know that the G to that central element going to act by a scalar k, and that basically gives you solutions of the polynomial x to the power k equal to lambda. These are the solutions which are going to be the eigenvalues for the matrix theta of G. And that basically says that since we are working over the field C, so there will be at most k many solutions, and that implies there can be at most mg many solutions. So the less than or inequality, it will always hold. The question is, can we characterize such that can we characterize the triple such that the degree is strictly less than mg? And in particular, they asked, can we consider elements of prime power and solve the question? And that's precisely what we do. Let me just go back and whether all of them can hear me. No, I see. Okay, sorry. Yeah. And also, please feel free to stop me at any place and ask me if you have any questions. Okay. So this was a question asked by T. Panjaliski, and we answered this question when G is a symmetric group and alternating group. So yeah, let's see the solution when G is a symmetric group. For lambda mu partitions of n, okay, before that I have to of course mention that all irreducible representation of Sn are indexed by partitions of n. So that's something I'm assuming. So with that, for a partition lambda, let's consider an irreducible representation rho lambda v lambda and any permutation of Sn with cycle type mu. We also assume that each part of mu divides mu1. You can notice that in particular when a permutation has has order some prime power, it's definitely going to satisfy this property. So in particular, the permutations having prime order is satisfying the hypothesis of the theorem. So yeah, so for these, the minimal polynomial will always be equal to x to the power order of u minus 1, except in the following cases. The case 1 is, of course, the trivial representation, and mu is not equal to 1 to the power, meaning any permutation which is not equal to identity. Then the minimal polynomial is simply going to be equal to x minus 1. And when the representation is, when lambda is n equal to n minus 1 comma 1, we get the standard representation of Sn. And when the permutation is n cycle, we have that the corresponding minimal polynomial is x to the power n minus 1 divided by x minus 1, which is also again has degree less than n. And the next case is the conjugate of the standard representation. And again, the permutation is an n cycle, and the minimal polynomial is x to the power n minus 1 divided by x minus the sign of the permutation, sign of the n cycle. And the fourth one is the sign representation. For this, of course, this is again a one-dimensional representation. So the minimal polynomial is just x minus the sign of the permutation. And there are these four are infinite families. By that I mean for each n, these four will exist. And there is some 5 many exceptionals, in the sense that these 5s are it won't occur like after n equal to n greater than 7, I believe. And yeah, so let me not read out those, but we can easily check for these pairs that the minimal polynomial is indeed these things, and each of them has degree less than the order of the permutation. And here somehow you can notice that it has a similarity to the classification of simple Lie algebras. There is 4 infinite families and 5 exceptionals. I mean, it's some coincidence. Okay, so the solution for the alternating group is also quite similar. It almost follows from the theorem for the symmetric group. Again, so when the representation is trivial, we have the minimal polynomial x minus 1, and the representation standard, we have the minimal polynomial x to the power n minus 1 divided by x minus 1. And again, there are some finitely many cases. Okay, so that's the one of our main theorems. Now let's again slow down a bit and give some definitions. So for a partition of n, we have semi-standard Young tableau. So an Young diagram of of shape lambda is an array of boxes with each row has lambda, the first row has lambda 1 boxes and the second row has lambda 2 boxes and so on. And this is what a shape of a Venn diagram of a partition is. And what do we mean by semi-standard Venn tableau? It's basically a filling from 1, 2 through n, such that when we read along the rows, it should be weakly increasing, and when we read down the columns, it should be strictly increasing. And that's what a semi-standard Venn tableau is. So by SYT lambda, we denote the set of all standard Venn tableau of shape lambda with entry from 1 through n, where each entry appears exactly once. And when it is semi-standard, we don't assume everything to appear exactly once. And for example, when lambda is 3, 2, we can see that we have 3 boxes in the first row and 2 boxes in the second row. So that's an Venn diagram of shape 3, 2. And you can see this filling is actually semi-standard, where the rows are increasing 1, 3, 4, and the columns are decreasing. For example, the second column is 3, 5. And a major index of a tableau, standard tableau in particular, is a sum of all I from 1 through n minus 1, such that the row of t containing I plus 1 should occur below the row of t containing I. And we basically sum all these i's and we get the major index. For example, for this tableau, we can notice that 1 is okay, so we say an entry I through y from 1 to n minus 1 is a descent if the row containing I plus 1 occurs below the row of t which contains I. So here you can see 1 is a descent, and we basically sum the descents, and that's what a major index is. So here 1 is a descent and 3 is not a descent because 4 occurs in the same row as which occurs as 3, and 4 is a descent because 5 occurs a row below to it. So here the descents are 1 and 4. So the major index is going to be 5 here. Okay, so let us denote this set of all standard Venn tableau of shape lambda with major index congruent to R mod n by A lambda R. And as I already mentioned, the major index of this tableau is 5. Okay, so we have introduced a combinatorial object. Now we relate this to a representation theory of symmetric group as follows. So Kraskevich and Weyman related this number to the representation theory of symmetric group by first considering a one-dimensional character Cn, which denoted by del r, which obtained by sending Wn to e to the power 2 pi ir by n. And with that, he's shown that this A lambda r is equal to the number of times V lambda occurs in the induced representation of the character del r from Cn from the, okay, I should mention here Cn is the cyclic subgroup generated by the n cycle to Sn. And with this, now we can go from a combinatorial object to a representation theory. And one can also notice that this A lambda r is equal to A lambda k whenever the greatest common divisors r comma n is equal to k comma n. I mean, one could see in variety of ways, in particular using the fact that the symmetric characters of the symmetric group are real valued. One can easily show that this holds. Okay. So So that basically connects the combinatorial object to the representation symmetric group. And now let's relate this to the representation theory of general linear group. Before that, let me introduce a bit of notation. So for a vector space V, consider the GLV modules, the tensor algebra TV, and the freely algebra LV and V. So the freely algebra, or simply the Lie algebra LV, is nothing but we consider this TV as a Lie algebra. As we all know that TV is an associative algebra, so we can see every algebra in particular as a Lie algebra. So we see TV as a Lie algebra, and the LV is nothing but the sub-Lie algebra of TV generated by V. And it turns out that it's a free Lie algebra on V. So in particular, we can also notice that TV is a GLV module, and this LV is also GLV module. Yeah, and also LV has a nice decomposition as where each nth component L and V is equal to P and V intersection with L. So one can naturally ask, since now we have a smaller representation, namely L and V, now what are all the irreducible components of it? So we have two GLV modules, L and V and T and V. And so we can easily see that what are all the irreducible components of T and V, because it's just a tensor algebra, and by Schur-Weyl duality, we can see that each W lambda, where lambda is a partition of n, having at most dimension of V parts, then the W lambda occurs in T and V precisely F lambda many times, where F lambda is, for example, K lambda round to the power number of standard in tableau of shape lambda. And now we have a sort of a smaller submodule L and V. Now one could ask, okay, so since L and V is also a GLV module, what are all the irreducible components, and each of them, how many times each of them occurs? So that's precisely what I mean. This is done by Klyachko, and he first did that by relating the representation of general linear group to that of symmetric group. So he has shown that the number of times W lambda occurs in the nth component of the free Lie algebra is nothing but the number of times V lambda, where V lambda is a spec module corresponding to the partition lambda of n, in the induced representation from Cn to Sn, where W denotes a faithful character, any faithful character of the cyclic subgroup generated by the n cycle. Okay, so now this boils down to showing the positivity, or basically the positivity in the symmetric group. So if we show that V lambda occurs in this, meaning this quantity is positive, then this theorem basically tells us that definitely W lambda also going to occur in L and V. And that's how he basically shown that he basically solved the problem of what are all the irreducible representation of W lambda which occurs in L and V. And in particular, our main theorem also solves the positivity of this problem, because this is essentially showing that an n an eigenvalue to e to the power 2 pi I n, for example, whether it's an eigenvalue for rho lambda of W mu, Wn or not, where Wn is and IMSc. So yeah, like I mentioned, he solved solve this problem for symmetric group. With that, he was able to show the so more precisely, this is what this is what he answered for the problem symmetric group. Namely, you take any partition of n greater than or equal to 3, then every irreducible representation of Sn contains a faithful representation of Cn, except when in these exceptions. And what you can notice that our main theorem also tells the same, but surprisingly, the proof is different. Okay, so let's see what are all we proved. What for which theorems we gave a new proof. Okay, so with these two theorems, with these two theorems, he was able to show what are all the irreducible representations of GLV which occurs in LNV. And we already know that the irreducible representations of GLV which occurs in TNV are nothing but it's basically all possible sort of homogeneous irreducible representations of homogeneous of having degree n basically. Okay. So W lambda occurs in TNV where lambda is a partition of n and the length of lambda is less equal to dimension of it. But we just shown that with the theorem on the symmetric group, all irreducibles V lambda also occurs except when lambda equal to n and 1 to the power n. So that basically translates into lambda equal, basically it's translated into Wn and W1 to the power n, which is basically the symmetric symmetric power of V, which is Wn, and the exterior power of V is W1 to the power n. So these two are the irreducible representation which won't occur in LNV, but all the remaining irreducible representation will also occur in LNV. Okay.
I think you want n greater than or equal to 7. Because n is.
Wait a second. Oh, that's true because there is a 2, 2, 2, 2. Sorry. Yeah, you're right. Sorry. Yeah. Thanks.
Sorry.
Okay. So and we basically by reproving the theorem, we also get to prove the celebrated result of Klyachko with this theorem. Namely, we sort of give a new proof of this result with, of course, using the another theorem of Klyachko. And we would also like to note that the solution of the problem of symmetric group by Klyachko uses only representation theory. And now we could ask that, okay, so he considered faithful representation of the cyclic subgroup. And we could ask, okay, we consider all possible one-dimensional character of the cyclic subgroup Cn, and we induce to Sn, and like what is the positivity there, and just using representation theory, because Klyachko has used only representation theory, so we thought one should also be able to prove only using representation theory, and that's what we actually do. Okay, so the goal is to prove the complete result for r greater than equal to 1 only using fine. But if you would like to see a purely combinatorial proof, then you could see a paper of Johnson who actually shown the positivity or given an algorithm which gives you a standard Young tableau of shape lambda with major index congruent to R mod n, where R is any relatively prime number where R is any number relatively prime to n. And of course, when the exceptions, excluding the exceptions noted in the theorem. And if you would like to see more proofs of the theorem of Klyachko, basically this theorem, you could see, I believe this is, okay, I forgot the name, sorry. Yeah, you could see in the references. Okay, so when we restrict our theorem to the n cycle, we actually get a theorem of Swanson. We basically give a new proof of his result, which is as follows. Yeah, so, okay, so maybe I won't read this, but yeah, this is just a special case of our main theorem for the n cycle. So, but I would like to note that this in particular proves the conjecture of Sundaram. And so we would also like to note that the proof of this theorem, which is proved by Swanson first, and then a year later it was proved by Yang and Starletov, who actually proved a little more general result. And their proofs only uses mostly asymptotics of characters and some bit of number theory, and it's, at least for me, it's hard to understand. So we give a proof which only uses representation theory and combinatorics, and we believe this is a bit more accessible than theirs. At the same time, we will also note that this basically this theorem basically ensures that a lambda r is positive in most cases, but this comes from the symmetric group side. But one could still try to construct a standard n tableau of shape lambda with major index congruent to R mod n. Oops. Major index congruent to R mod n. By that I mean giving a sort of combinatorial algorithm to construct such a tableau. But when R is congruent to, when R has GCD, it's relatively prime, then it's given by Johnson, which I already mentioned. Okay, so yeah, we gave a proof, nice proof. And yeah. So what's the conjecture of Sheila, which, where we used representation theory to prove it? That's as follows. So she considered a trivial representation of the cyclic subgroup generated by the n cycle, and she induced to Sn. And the question is, what are all the irreducible occursive? So she basically remarked that the irreducibles are going to correspond to n minus 1 comma 1 when n greater than or equal to 2, and 2 comma 1 to the power n minus 2. Okay, the irreducible correspond to the partitions, these. And when n even, it's going to be the sign representation. So again, in particular, the restriction, the special case of our theorem gives a new proof of the conjecture of Sheila proved by Swanson. Okay, so we've also considered invariant vectors in Sn in a recent paper, where we get to prove for a general permutation of Sn, and we ask whether this matrix has eigenvalue 1 or not. So we basically consider whether the determinant is non-zero. And we actually shown that these are all the exact exceptions. Here also you could notice sort of 4 infinite families and 5 exceptionals. And here the base case is given by the, it's basically the conjecture of Sundaram. But that was again, basically the Joshua's theorem is the base case of this theorem, and I mean that we couldn't prove at that time, but the remaining is just using little Richardson keep repeatedly. We get to show this theorem. But now with this paper, I mean, proving in particular for the n cycle using combinatorics and representation theory, we sort of complete the picture of the whole theorem just by, I mean, so basically we complete this whole proof only using combinatorics. And similarly, we done the same for the alternating group as well. Okay, I should have mentioned this is a joint work with Amritan Suprasad and Namruta P. And similarly, we consider the same problem for the alternating group, basically finding non-zero invariant vectors in the irreducible representations of AN. And we get to show that these are all the exceptions. Again, we mentioned that here the base case is when the partition has length 1, which is an n cycle, and for the n cycle, Yang and Starletov already shown when it's going to have a non-zero invariant vector in V lambda, so which we use to show for a general permutation. But again, with this paper, we also, I mean, complete the picture only within the same framework. Okay, so there is also one more counterpart which we proved in this theorem, namely, we consider permutations having even order, and okay, so we consider the questions like invariant vectors. What about the other extreme? Namely, for an even order element, we know that -1 could be an eigenvalue, but precisely that's what we ask. Do you have a non-zero vector V such that rho lambda W mu V is -V in V lambda? Equivalently, again, whether -1 is an eigenvalue for rho lambda of W mu. And we show that it's in fact true. It's going to be it's always going to have, except in these exceptions. And for alternating group, we have even more nice theorem. It says that you take any alternating group, but it's actually, let's assume that let's take that we take any simple alternating group equivalently n greater than or equal to 5. Then for all non-trivial irreducible representations, we always have an anti-invariant vector. I mean, quote unquote anti-invariant. By that I mean, yeah, there is a vector V such that rho lambda W mu is -V for even order elements. W mu has even order. Okay. So what is the proof of all those? So until this is just sort of an overview of whatever we have done, and I mean, how did we sort of give new proofs to the other things and some completeness of theorems only using rep theory. So now let's go to the sort of a proof of it. So one of the main tool is the little Richardson rule, which states that let mu be any two partitions of M and T, then the S lambda denote the Schur function correspond to the partition lambda. Then S nu is equal to the little Richardson coefficient C mu nu lambda, S lambda, where lambda varies for the partitions of M plus T, where the C mu nu lambda is going to be the number of semi-standard Young tableau of shape lambda mod mu, and with content nu such that the reverse row reading word is a lattice permutation. By word is a lattice permutation, by I mean if word is like W1 to Wn, then you stop at, I mean, you read from left to right and you stop at any stage, and now you see, I mean, now it should satisfy that the number of I must be greater than or equal to number of times I plus 1 occurs. So that's what a lattice permutation means. And the reverse rotating word, I mean, we read the entries of the tableau from top to bottom, from right to left. So that's what a little Richardson coefficient means. If you want to see an example, we have that we consider S22, S21. Then let's say S322. Then so we have to consider a shape lambda mod mu, where here mu is going to be 22. So we have these 3 boxes left over. Now we have to fill with the content 2, 1, which means we have to put too many ones and 1, 2. So the reverse rotating word implies, I mean, the lattice permutation condition implies the first entry must be 1, because this is what we start with. I mean, the word is going to start with the entries in the first row. So of course we have to put 1, otherwise the first condition itself will fail. So that there we have to put 1 only. And in the other entries, now we left out with 1. I mean, we have to put 1 many ones and 1 many 2. So, and the semi-standardness implies there is only one possibility, 1 and 2. So there is only one such tableau possible with all the properties satisfied. So this occurs with multiplicity 1. So that's what the Littlewood-Richardson rule is. And interestingly, the proof, the wreath product is used very extensively. So let me just brush upon that. So for a subgroup H and a subgroup K, where the subgroup H is a subgroup of Sn and K is a subgroup of Sm, then we have a natural embedding H wreath K to Smn, where H wreath K is equal to H to the power n semi-direct product K, where K is going to act on Hn by permuting indices. Basically, yeah. And the embedding given as follows. So we take an element f comma pi and we send it to the following permutations. So first we split this mn many object to m many blocks of each where each block of size n. 1, 2. Is there any question? Okay, sorry. So yeah, we split this mn many objects into 1, 2, and so on n, and then n plus 1 through 2n, and so on, n minus 1 times m plus 1 to nm. And where each now each I mean the elements of Sm going to act by permuting these blocks. So what do we do is we take a generic element of the form j minus 1 times m plus I. Then we first permute the block by the permutation pi, and then we act it on I as by the permutation on the jth pi jth component here. Okay, I should have mentioned the f is basically, you could see it as a, I mean, it's an n tuple, but in particular you can see it as a function from n to, oops, it's actually m to n. Okay, so this is how we see a subgroup H of Sn and K of Sm where the correct, so we see the subgroup H wreath K into SMN. Okay, so yeah, so the one of the very important lemma is where where this lemma allows us to use induction in our proof of the main theorem, which is Cn. Where Cn is a subgroup of Sn and Cm is a subgroup of Sm, then under this embedding, the Cm wreath Cn contains an Mn cycle. More precisely, if you consider, for example, a permutation, an element of Cm wreath Cn as follows. Namely, you take the first component, an M cycle, and then the remaining component, all are identity, and the permutation on Sn to be, pi to be, for example, 1 through n. Then the image is going to be this long NM cycle. Okay. So another thing is the proportion, which is sort of a pillar of a proof, where this just sends us to go to combinatorics and just use little Richardson to show whatever is required here. So let del be an irreducible character and P be a prime and n is equal to MP. Here you could note that we are assuming n to be composite, and when n is a prime, then the main theorem is very easy to prove. So we assume that, not the main theorem, the theorem of Joshua is easy to prove. So we assume that n is composite, and yeah. So the next thing is we also assume that there exist p many partitions of M, with not all of them being the same, such that for 2 less equal to I less equal to P, we assume that the restriction to the M cycle contains a trivial representation of it, and the first component, when we restrict the first component to, Sm to Cm of the first irreducible chi mu1, then the character del P occurs, where the del P is a one-dimensional character of Cm obtained from this delta just by restricting Cn to Cm. Since n is MP, so you can naturally see this Cm as a subgroup of Cn. Okay. And finally, of course, let lambda be a partition of n such that when we restrict this irreducible representation V lambda to the Young subgroup Sm to the power P, then we assume that this irreducible representation chi mu1 tensor chi mu P occurs. And in this case, the implication is as follows. We have an irreducible, a representation, a sub-representation, which is induced from Cm time, the product of cyclic subgroup Cm p many times to the Cm wreath Cp of the representation del P tilde, which is given as simply on the first component, it is the del P, which we already obtained by restricting del, and the remaining components we simply take the trivial representation. And this representation is going to occur as a sub-representation of the restriction from C, this symmetric group to the wreath product. And if this whole, this is one implication, and now simply using Mackay's restriction formula, we get the required result for us. So now with this theorem, we can note that all we need to do is, for a given partition of n, we have to show that there exist partitions mu1 through mu p satisfying all these conditions. Then we can easily see, then using this theorem, we can show that indeed all these one-dimensional characters of the cyclic subgroup Cn occurs in the restriction. So idea of the proof is roughly basically this. So we start with the partition. I mean, we start with the irreducible representation chi lambda of Sn, and we also know that there exists an irreducible representation chi mu1 through tensor and so on, tensor chi mu p, where the restriction is positive. And we also know that any irreducible representation of Sm wreath Sp is going to look like some induction. And we know that this restriction contains chi mu1 through chi p, which means it must come from some irreducible representation of Sm wreath Sp. But we also assume that not all mu i's, the partition mu i's are same. That allows us to that the representation which occur, I mean, which is sort of in between Sm wreath Sp, which is in between Sn and Sm to the power p, which must look like some induction from a smaller subgroup Sm wreath I. Also, the fact that mu i's are not all of them are same implies that this I is an Young subgroup, and in particular, it's a proper Young subgroup. By I mean it's not equal to Sp. So that basically essentially allows us to use Mekes restriction formula at the double coset equal to identity to get that this representation is a sub-representation of chi lambda restricted to Cm with Cp. That's roughly how the proof goes. And now we sort of came to the literal Richardson part, where we simply consider the product of the Schur function over and over to get the result. May I know how much time I have?
Yeah, about 5 minutes.
Okay, so yeah, so maybe let me. Okay, so this is one of the.
I'm sorry, can I ask a question?
Yes.
I think, sorry, I think I missed the definition of delta P.
Okay, so that's simply, okay, so maybe I can write somewhere. So the delta P, this one or the tilde one?
This one.
Okay.
I'm not
This one.
sure I saw that.
Okay, maybe let me go to the slide, yeah. Is this okay? Where is it?
It's your third. It's in your third bullet point.
Third bullet point, huh? Oh, this one.
Yeah.
This is just the restriction. I mean, you restrict from Cm to Cn delta. So this, I mean, sorry, I'm doing the other way. Cn to Cm. So, I mean, of course, Cm is not going to be a subgroup of Cn, because Cm is generated by 1 through m, but you see an isomorphism copy of it in Cn. Basically, we know that n is mp. So when we
okay, yes,
yeah, when we just raise the permutation to the power p, we get a product of m cycles.
It's like the diagonal subgroup.
Exactly. It's a diagonal subgroup, but with that we basically get a representation for Cm.
Okay, great. Thank you.
Yeah. Thanks.
What I was missing.
Yeah. Okay. So this is one of the important lemma, namely, I mean, this is actually sort of fairly obvious. I mean, for a partition of p plus q, of course, we know that if we have a partition alpha of p which contained in lambda, then of course there is going to be a beta such that the corresponding literal Richardson is possible. I mean, this is always possible, but we give a very a strict way of doing it, or a very algorithmic way of doing it, which reduces the calculation a lot in our proofs. Namely, what we do is we consider the skew tableau lambda mod alpha, and we fill the shape of lambda mod alpha as follows. you take any column of the skew shape, and you just start filling entries like 1, 2, and so on. And this filling is going to give you a semi-standard rank tableau with the reverse rotating over as a lattice permutation. So this is one of the very important lemma. And yeah, so I'm running out of time, so let me just sort of brief through how the proof of the theorem goes. So this is, as I already mentioned, is essentially by an induction. I mean, one can easily verify when n is less equal to 26, the theorem gonna hold. So let's assume that case greater than n. So I think we let's assume that first n is prime. So for prime, let's consider the matrix rho lambda of Wn. So in this case, we assumed n to be prime. When lambda is not a Hooke partition, we know that by recursive Murnaghan-Nakayama rule, the corresponding character value is going to be 0. So that implies that since we also know that the only possible eigenvalues for the matrix rho lambda of Wn are the pth root of unities, and the character value is also 0, implies that implies that 1 and the non-trivial pth root of unities all must occur. And similarly, when it is a Hooke partition, one can easily show that except when the dimension is n minus 1, less than or equal to n minus 1, both pth root of unities, 1 as well as non-trivial pth root of unities must occur as an eigenvalue. And when n is a composite number, we simply use the proportion and the Little Richardson to show an existence of the mu1 through mu p, which satisfies all the required conditions of the proportion. Yeah, and these are all references. Thank you.
Thank you for the talk. Are there any questions?
I have one question.
Yeah.
So, okay, I don't know much about algebra, but basically what you're doing is you're taking a representation that means sort of to each element of the symmetric group for that particular representation, you have a matrix and you're looking at the minimal polynomial, right?
Correct.
So, do you think there are other interesting polynomials that you can look at and study, like other than the minimal polynomial?
Oh, okay. So, ideally, one would be really interested to study the characteristic polynomial because, a theorem of Joshua. Joshua has not just proved the positivity of the existence of standard M tableau. He also shown some nice equidistributions on the eigenvalues. So ideally, one is really interested in that, but yeah. So yeah, studying his characteristic polynomial is, I think, slightly more harder. But yeah, people are interested in that as well. Yeah.
Okay, thanks.
Yeah.
Can you use this now to determine the global conjugacy classes in AN?
So that's essentially so for that we need we just need the eigenvalue 1, right? And we only considered partitions where each part divides the largest part, which means the cyclic subgroup is just going to be have order equal to the largest part. And And the centralized, but if you consider the centralizer, on the other hand, that's gonna be huge, right? Centralizer of W mu. So I mean, what I'm saying is our result is not going to give us much because the induction is larger compared to the induction from the centralizer.
Okay,
So
yeah.
that's, I mean, that's true, but yeah. But I mean, I believe, do you have any conjecturally any prescription for the global conjugacy class of A? Because it's, I mean, I've tried, but I couldn't even come up with some nice conjecture for the global conjugacy class of A.
I haven't thought about it in a while, so I'll have to look at my notes.
Yeah.
Thanks.
Yeah, thanks for your question. Yes, Aditya. I think you have to unmute your.
Thank you. I had a question about the alternating group representations you were talking about. Could you go back to the slide?
Yes.
The result on alternating group was like
Mm,
60 something.
yes. So is it about the invariant vector or about the
The invariant vector.
anti-invariant vector? Sorry?
Yeah,
Anti-invariant.
it was around slide 60.
60. Okay.
Yeah. Like on the bottom of the slide.
Mhm. Okay.
Yes.
So yeah, this is for the
Right. So
eigenvalue 1. I mean, basically finding non-zero invariant vectors. Yeah.
So here the representations are, you have a plus minus representation. So
Okay. I should mention. I mean, here. I mean, so the Sn irreducibles are indexed by partitions of n, but the n irreducibles are, I mean, almost, but not quite, because when lambda is equal to lambda prime, where lambda prime is the conjugate of the partition lambda, when you restrict v lambda to an, it's no longer irreducible. It splits as two inequivalent irreducible representations, and we call one of them plus and other is minus. So
right.
that's what
And
are those.
and so when it's not self-conjugate,
It's always, it remains irreducible.
okay, it remains irreducible. Cool.
Yeah.
Okay.
Yeah, you basically want to think about a conjugacy class when a conjugacy class in Sn is also a conjugacy class in An or not.
Yeah,
So
that's
Okay.
it's not, it splits into two.
yeah. Precisely when the permutation has distinct odd parts, and that those are also the global conjugacy classes indexed by when it has length at least 2, which is proved by Sheila. Yeah.
Okay, great. Yeah. Are there any other questions? If not, we will thank Velmurugan again. Thank you for the talks.